Hi, my name is Michael de Podesta, and a couple of weeks ago I gave a talk to some school children, sixth formers at a school in London, and I just thought I would go through the slides I gave there and distribute it to a slightly larger audience. So this talk is aimed at sixth formers, and it's assuming they've got some sort of general ideas about physics and some ideas about maths. So it includes a little bit of maths and sciencey things, but not too much. So I hope it's be accessible to perhaps more people than sixth formers, but that's who it was originally targeted for. And it's about climate change. It's got two parts, and the first part is explaining what the problem is and how urgent it is, and the second part is about some of the things that we have within our control right now that we can do about the problem. So let's start. So what is the problem? Well, people have heard the problem explained in many different ways, so I'd like you to begin by just thinking about this, looking outside, and in general what you see, if you look up at the sky, is you see clouds and you see blue sky. Those are in some combination. So let's just take a look at those. Let's take a look at clouds. So we know where clouds come from. 2/3 of the planet's surface is water. The sun shines, water evaporates, rises up in the atmosphere and condenses. It condenses into lots of tiny droplets. They're typically a thousandth of a millimeter to a few thousandths of a millimeter sort of size. And one of the curious things is, why do clouds look the way they do? Why are they white? Remember, water is transparent. So why doesn't the light just come straight through? Well, it's the same way that foams look white when when a wave crashes. It's due to scattering of light. So sunlight shines on the clouds, and you can imagine a particular ray striking a little droplet there, and in general a little bit will get reflected, about 4%, and some will be transmitted in some particular direction, and then some of that will get reflected and then transmitted in a different direction. And it doesn't take very long before the scattering of these droplets ends up with light coming out of the cloud in all directions. So that's why clouds look white no matter which way you look at them. Now, if it gets very thick, the bottom of the cloud can look grey because there's not much light making its way through, but the tops of the clouds always look white. So when we look up, we see clouds, and that's why it's this scattering process. So let's take a look at the other thing we see, which is blue, and that's also due to scattering, but it's a different type of scattering called Rayleigh scattering. Scattering is a word that just means that the light ends up going in a different direction, and that's caused by the fact that although the air in the atmosphere looks transparent, it's not completely transparent. When light shines through it, it causes the air to literally glow with a very, very faint light. So what happens is, as the light comes through the air, the light is a wave in the electric field, then the atoms in the molecules of oxygen and nitrogen that make up most of the atmosphere, the electrons on those atoms move up and down. So you get this sort of little wiggling. And because there's an electric charge moving up and down, that sends out its own wave. Now, this happens more strongly for blue light than red light. So when we look up in the atmosphere, instead of looking through a transparent atmosphere out into the blackness of space, what we look up and we see this faint glow of the air caused by sunlight traveling through it. That's called Rayleigh scattering. So those are the two things that we see if we look up at the sky. But if you looked up at the sky in the infrared, the sky would always look foggy. You will get none of this type of stuff. It would look like fog every day. So I'm just putting some fog on here to remind you what fog looks like. Here we go. And you can perhaps still see some of the writing there. So let's make it even foggier, because the atmosphere is actually completely opaque in the infrared. I'm recording this on the day that the James Webb Space Telescope is releasing its first images, And the reason it has to be placed a million miles from Earth is to get out of the Earth's atmosphere, because from Earth we cannot see through the atmosphere in the infrared. It's permanently foggy. So this so-called infrared fog is caused by the presence of several gases in the atmosphere, the most important of which are water, H2O, and carbon dioxide, CO2. And the reason it looks foggy is, again, a different type of scattering. So here's an infrared wave. It's got longer wavelength than the light wave. And instead of that's too low a frequency of vibration to shake the electrons on atoms very much. But what it does do is it shakes, it causes resonances in the way molecules vibrate. This is a water molecule, you see, and it's got this particular frequency of vibration, particular mode of vibration. And when the frequency of this wave just matches the resonant frequency, you get this scattering. This starts moving, and the charges on the atom then re-radiate the light in all directions. And this is so strong for these gases, it makes the atmosphere opaque to infrared light. So this absorption and re-emission makes the atmosphere opaque to infrared light. And the key thing is the density of this fog depends on the concentration of both water vapor and, critically, CO2, carbon dioxide. So the thickness of the fog in the infrared depends on the density of carbon dioxide. So let's talk about the concentration of carbon dioxide in the atmosphere. And there are two ways to talk about it. First of all, let's talk about the fraction of the atmosphere that's made of carbon dioxide. So if you were to catch 100 molecules from the atmosphere, you'd find about 19 molecules of oxygen, about 80 molecules of nitrogen, and about 1 molecule of argon. You wouldn't catch any carbon dioxide molecules or water vapor molecules. But if you looked at about 1,000 or 1,200, you typically see about 4 water vapors, but you still, on average, wouldn't catch a single carbon dioxide molecule. It's not until you look at 10,000 molecules that you can see the carbon dioxide molecules, and here you can see them quite clearly. Now, just in case you can't see them quite clearly, here they are, and let's just make them grow and wiggle them about a bit. There we go. And that's typical of the concentration in the atmosphere currently. There are 4 carbon dioxide molecules in about 10,000 air molecules. So if we had 100,000 air molecules, there'd be about 40, or 400 in a million air molecules. So that concentration, we refer to that as 400 parts per million, or 400 ppm. Okay, so what is the atmospheric concentration of carbon dioxide? Well, this graph shows the atmospheric concentration of carbon dioxide from 1700 up to the present day. And these are the ppms, 200, 300, 400. And currently we are at about 420 parts per million. And this concentration in the atmosphere is increasing at about 2 parts per million per year, very roughly. But you can see that historically, the historical concentration was 280 parts per million and stable, so back several generations ago. Now, this increase here in carbon dioxide concentration is increasing the density of this infrared fog, making the atmosphere more opaque to infrared light. So why is that happening? What's causing this increase? Well, I'm afraid we have to switch now to looking at amounts, the actual amount of carbon dioxide in the atmosphere in tons. And the answer is it's us. It's you, me, our families, the way we live. We are putting massive amounts of carbon dioxide into the atmosphere. So this is the yearly human emissions of carbon dioxide. This is billions of tons per year. 1 billion tons of carbon dioxide, a gigaton, is an almost unimaginable amount of carbon dioxide. I won't try and give you some analogy, it's just mind-boggling. And this is again from 1700 up to the present day. And you can see that roughly now we're putting 36 billion tons of carbon dioxide into the atmosphere every year, which is a tremendous amount. So let's take a look at that in the context of the amount of carbon dioxide that there is trapped in different places on the Earth. So this graph and the following figure, all the numbers are approximate. It's not the exact numbers that matter. It's the rough magnitude, and they're all in billions of tons of carbon dioxide. So keep in mind that 36 billion tons that we're putting into the atmosphere. So the amount that's in the atmosphere, well, the amount that was in the atmosphere in 1800 was about 2,000 billion tons. But there's loads in the deep ocean, about 143,000 billion tons. And in the upper layers of the ocean that mix with the atmosphere, there's about 3,600 billion tons. And in the growing things on Earth, there's about 1,830 billion tons of carbon dioxide. And in the soil and the humus in the soil, the organic matter there's about 7,300 billion tons of carbon dioxide. And every year back then, all the time, there's a natural way of exchanging things. So as the atmosphere, where it meets the water, you get bubbles of the atmosphere encapsulated in the surface, and gas can go from the atmosphere into the liquid, and from the liquid into the atmosphere. So there's a constant flux of about 330 billion tons every year. And similarly, when things grow in the spring and summer, we absorb carbon dioxide from the atmosphere and make a biomass. And then in the autumn, it's emitted again. So there's this constant cycle. So let's see how that has changed in the modern day. So what we have done in the Industrial Revolution is we've gained access to these reservoirs of massive amounts of coal and amounts of oil and gas. And we're tapping into them, and we're emitting 36 billion tons a year. So you can see 36 is smaller than all the numbers on here. It's not negligible, but it's not dominating these numbers. And so what happens to the amount that we put in the atmosphere? Well, very roughly about 9 billion tons goes into growing extra things. So about 9 billion tons goes into growing things. About 9 billion tons gets captured in these upper layers of the ocean, and that's affecting ocean acidity, another problem, but not today's problem. And then the residual, which is about 18 billion tons, is left in the atmosphere. And so now there's about 50% more carbon dioxide in their atmosphere than there was in the 19th century, and it's increasing at about 18 billion tons per year. So why does this concentration of CO2 in the atmosphere matter so much? Well, it's about the temperature of the Earth and how the Earth comes to be the temperature that it is. So here's the Earth in space, and you can see basically you can't get any matter off the Earth. It's very, very difficult to get matter off the Earth. The only way to get energy in or off the Earth is by radiation. So we know that we're very grateful to the sunlight, which comes from the sun and warms the Earth, and the Earth warms up. And as it warms up, it doesn't get hot enough to emit visible light, but it gets hot enough to emit infrared light. And when the amount of energy coming in from visible light is balanced by the amount of energy that goes out from visible light, then the Earth's surface temperature will stay constant. So it's all about balance. So here's the heat input from the sun, and you can see that's pushing up the Earth's temperature. And here's the heat lost from the Earth. So this is the situation when these two quantities are in balance. And just for scale, let me show you on the same scale all the energy that human beings use in a year. Here, can you see it coming down here? That's world energy production. It amounts to just over 1/10,000th part of the heat input from the sun and the heat that's radiated every year. And in fact, to be honest, I've drawn it a bit too big, so let's just draw that to scale. So there it is, that's drawn to scale. That's human energy use compared with these two balances. And so the problem with the carbon dioxide, as we'll see, is it's going to affect this heat loss from the Earth. So here are some numbers now. On average, the sunlight provides about 240 watts per square metre of the Earth. That's averaged over the whole Earth's surface of summer, winter, day, night, poles and so on. And what that does is it warms the Earth up, and the Earth warms up, and we have to lose, on average, 240 watts per square metre in order to establish a stable temperature. Now, if there were no atmosphere, this process would go on, and we know the temperature of the Earth. We can do the physics for that. It would be minus 18 degrees Celsius. It would be a very difficult place to live. But thankfully we have an atmosphere, and it's filled with carbon dioxide and water vapor, and they re-radiate. One famous scientist called this sky radiation. So the fog, some of the bright infrared light from the Earth gets re-radiated back, and that amounts to about 150 watts per square metre, and that provides what's called the greenhouse heating of the Earth, and that amounts to about 33 degrees Celsius, or it did historically. And what we're doing is we put this extra bit of CO2, there's about 50% more CO2 than there was, and that's providing a little bit extra sky radiation, just over 1% of extra sky radiation, and that's causing the Earth to heat up by a degree or so. So what we're doing is, it's not the energy production of the Earth that's the problem, it's the fact that what we're doing is affecting the balance between the heat input from the Earth and the heat lost from the Earth. And because these quantities are so vast, we're able to have an outsized impact on the planet. So we're just tipping this like that. And here you can see, if you look at the records, this goes from 1850 to well, this one's going up to 2070, and this is the yearly data, and this is the 10-year moving average. And you can see if things keep going like they are, we're going to really warm up very, very quickly. This is called the global temperature anomaly. That's the temperature difference from this period, from 1900 to 1850. And let's just take a look at what some famous people said about global warming through history. So here in 1898, Svante Arrhenius said, if we ever managed to double the concentration of carbon dioxide in the atmosphere, the Earth would warm by about 4 degrees Celsius. But we weren't emitting very much back then, and it seemed fanciful that we ever could emit enough to ever warm the Earth. But people didn't worry about it because they thought it would be a good thing. Being a little bit warmer is generally a bit nicer. In 1937, UK scientist Guy Callender pointed out this warming here, and he said, I think that's caused by the carbon dioxide we're emitting, and it's going to warm us up. It has warmed us up already, but at 5 billion tonnes per year, this won't bother us for a few hundred years. And he was certainly right about that. But then in 1981, James Hansen said, we will be in big trouble if we don't reduce carbon dioxide emissions urgently. This was when we first learned to really model how the atmosphere worked. So these are famous people. Let's take a look at some less famous people. This is a person I'm very fond of. This is me. I was born in 1959, and I'm planning on dying in 2040. And you can see that at the end of my life, we're looking at a world where you can see that this whole process here seems to have taken place during my lifetime. And I can tell you, I personally can notice the difference in the climate. It's just much warmer. And then there's your lives. Well, your lives, I don't know what it's going to be like in your lives for teenagers now. I hope that we will do something to change the course of this curve. And in what I'm going to tell you about it, I want to tell you how to do that, what you need to do. Now, the world's warming up and there's this nice straight line, but that's not what you experience. What you experience are headlines: Japan swelters in its worst heat wave, Europe heat wave, and you get these extreme temperatures. That's the first thing you know. And right now it's a really hot day. It's 33 degrees in Teddington. We're looking at even higher temperatures at the end of the week. And what you see are these news, and this picture of the Earth here is from 2021, and it shows areas of the Earth that experienced their hottest year ever in the records. So that's the hottest year. And then in the lighter shade of red, those are years that experience their second hottest year, third hottest year, fourth hottest year, fifth hottest year. And you can see all over the earth, places are experiencing their hottest ever year. And on the same graph, we have places that experience their coldest year, their second coldest year, their third coldest year, their fourth coldest year, their fifth coldest year. And you can see there are no places that experience their coldest year. The whole earth is warming up. Next year, the places that, like, which is this year now, the places, 2022, the places that experience their hottest temperature will be slightly different. But if you can just imagine, slowly, everywhere is warming up. So let me just show you what you need to do to limit global temperature rise. So these are annual CO2 emissions. So you remember we're back at 36 gigatons, 36 billion tons, and this is from the year 2000. This shows the historical record. So that's now. So we're currently emitting 36 billion tons a year. And in order to limit warming to 1.5 degrees Celsius on average over the globe, we need to be emitting following this curve. We need dramatic cuts absolutely immediately. So to limit warming to 1.5 degrees Celsius, we can only emit another, that's the whole Earth, another 500 billion tons of CO2. To limit it to 1.7, we've only got another 850 billion tons. To limit it to 2 degrees, we can only emit another 1,350 gigatons. So just to tell you how long that is, if we don't do anything, at 36 billion tons a year, that's 14 years. So this is going to happen in your lifetime. Are we on the green curve? We are nowhere near the green curve. This black curve is probably still rising at the minute. We haven't even gone flat. So this is a desperate situation. And if you don't want the earth to warm, we need collectively to do something about it. So this is the summary of this first part of the talk. The climate that your parents grew up in is gone. It's gone forever. It will never, ever return. However hot the earth gets due to what we do, it will never cool down. That's it. Even if we emit zero carbon dioxide, the earth will not cool back to its pre-carbon dioxide boost for millennia, if ever. So as hot as we make it, that's as hot as we're going to have to live with it. If we try very hard, we can still avoid the worst outcomes. We just have to stop emitting CO2. Just stop emitting CO2. So I would ask for questions now, but I'm just sitting alone in my front room, so let's move on. So we're now going to come to the second half of this talk, and what I'm going to do is I'm just going to pause the video to give myself a chance to have a cup of tea, and then we'll go on to some of the things you can do about it, or your parents can do about it within their own home, how this is going to affect the way we live in our own homes.